All right, so this is a talk about fuzz testing Soroban smart contracts. It's going to be technical, not super deep. It usually lasts between 30 minutes and 50 minutes. We can do QA at the end, though if people want to interrupt and ask questions, I'm down with that. So my name is Brian. I am a expert in the Rust programming languages. I've worked with Rust for 13 years. For 7 years, I was on the team that built Rust. I've been working on fuzz testing support for Soroban this year, and this talk kind of encapsulates everything I've learned about it. There's a fuzz testing tutorial on the official docs website, and I'll have a link to that at the end of this. Some of the topics in this talk are covered in the tutorial in more depth. Okay, so this talk is in 4 parts. The first part is about Rust fuzz testing specifically. I'll try to get through that fast, but it's necessary background info. The second is specifically about fuzz testing Soroban contracts. And the third section is the meat of the talk, where I give a few tips, best practices I've learned about fuzz testing smart contracts for Soroban, which is sometimes different than fuzz testing other types of programs. Section 4, I might talk a little bit about some of the results we've had with fuzz testing. I might just skip it. It's not a great section of the talk. So fuzz testing is a very particular type of testing. It's useful to contrast fuzz testing with other types of testing, particularly unit testing, which is the most common type of software testing. With unit testing, you're generally writing a very small test code that tests a really small subset of your program. It just tests this one thing, and it tests that same thing all the time. And then you might, over time, write thousands of small unit tests for your program. Fuzz testing is very different in that you don't write a fuzz test that tests one thing. You're generally testing the whole program, and the fuzz test takes randomized input and generates randomized calls to your program. So in that way, it can test many different parts of your program, and the hope is that you'll test branches in the program that a human might not have thought about to test, or might not have considered when they were writing the code initially. Fuzz testing has the most important part of fuzz testing is it also includes a feedback cycle. When you compile programs for fuzz testing, your whole program is instrumented, and it actually keeps track of every branch the program takes. And so when the fuzz test is running, it generates random input, watches what happens in the program, and then based on what happens in the program, I might say, oh, this input generated a new branch. It found a new branch in the code. And it'll use that discovery to generate new random input. And it'll go in this iteration of generating input, watching what happens in the code, and going through iterations of many, many tests. With fuzz testing, you'll probably run 1 million tests at a time. Fuzz testing, though, is kind of inconvenient in that it's an exploratory process, interactive with the programmer. You kind of write a fuzz test that you hope will find some new branches in the code and dig up bugs. Then your fuzz test finds a bug. Then you go fix that bug, and then you'll maybe adjust your fuzz test, run it again for 1 million iterations, and on forever. There's kind of no end of the fuzz testing. Oftentimes, fuzz tests are thrown away once they found what they're going to find because they're kind of inconvenient to maintain and continue to run continuously, unlike your unit tests. Fuzz tests aren't usually part of continuous integration, but some people do fuzz tests continuously. Fuzz tests are a very powerful way of finding unanticipated behavior in your program, but they're not the most powerful proof of what's going on in your program. They just give you extra confidence about your program. They're not the same as a formal proof. A formal proof will say definitively this is what the code does. Fuzz tests just are good at finding a brute force way of finding many paths through the code. So some types of programs are better for fuzz testing than others. Some types are worth fuzz testing. Some programs aren't worth fuzz testing. In general, we fuzz test code that is exposed to untrusted user input and where there are high security consequences to failures. A lot of programs are not easy to fuzz test, but there are some kinds of programs that are very easy to fuzz test. In particular, fuzz tests accept random bytes as input. So programs that parse bytes like protocols, document parsers are really easy to fuzz test. And they're just no-brainers. You should definitely fuzz test those types of programs. Programs where they have multiple representations of the same data and you can do round-trip conversions between them are slam dunks for fuzz testing because you can just test that the two representations are always the same and can always be converted back and forth. Formats that have multiple implementations, like if you can compare against a reference implementation, that's an easy thing to fuzz test because you can throw random input at the reference implementation and your implementation and test that they both do the exact same thing. Fuzz testing is kind of an unbounded activity, so it's an expensive thing to do, and you never really know when you're done. So it's kind of hard to judge whether it's worth it to fuzz. Sometimes you never fuzz anything. You never find any bugs through fuzzing. So in the Rust world, we do fuzz testing with a tool called Cargo Fuzz. Cargo Fuzz is a command line wrapper around libfuzzer, which is the LLVM library for fuzz testing. And because Rust is built on LLVM, it's a natural fit. There are other fuzzers that work with Rust. Most of them are managed by the Rust Fuzz organization on GitHub. But Cargo Fuzzer is the one that we focus on. So real quick, I'm going to show you a little demo of just basic fuzz testing in Rust. All right, so what I'm going to test here is the ComRack Markdown parser. Markdown being a very simple document format. This program is going to be parsing just randomized input bytes as a document. And I just want to point out a few basic things about how Rust fuzzing works. So the first thing to notice here is that in the first line, we have a no main attribute. This pound bang here is a Rust attribute. This no main means we're not going to write a main function, even though the fuzz test is a standalone program. Instead, from libfuzzer sys, or Rust crate, we're importing fuzz target. Fuzz target here is a macro indicated by this bang. And this macro takes a closure, a Rust function, where the only argument is this array of bytes. So fuzz target is going to generate our main function for us. And it's going to generate a whole bunch of glue between the underlying fuzzing harness and our own test case. And there's nothing really interesting in this test case, but what we're going to do is we're going to parse this document from bytes into an in-memory representation, and then we're going to serialize it back out again. I'm going to run this with Cargo Fuzz. I'm going to say cargo plus nightly fuzz run. And this plus nightly is a bit of a magic argument that most Rust tools accept, that it selects the Rust toolchain. In this case, Cargo Fuzz only works with a nightly compiler, which is the unstable bleeding edge compiler. It's not compatible with the stable compiler like most of the Soroban tooling is. So we're going to say plus nightly fuzz run fuzz target 1. And this program here is the first fuzz target. It is fuzz target 1. And when we run it, we're going to see a whole bunch of spew. And I know this version of ComRack has a bug, and hopefully within a fairly short amount of time, the fuzzer will discover that bug. And you can see in the spew on the left-hand side, the numbers are going up, 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 up. So these are the iterations of the test. We've already run 25,000 iterations of this particular test, all with different input. And hopefully, usually it finds this bug very fast. When it finds the bug like it has, it dumps out a bunch of information about what happened. And I'm just going to point out a few things to note about this. If you go through the back scroll, when it finds the bug, and all these fields here, most of them I found not that interesting, but a few are interesting, like coverage. This is the coverage number. I think it's, I don't know, branch coverage or line coverage. It just goes up as the tests progress, and it gives you some idea of like whether you're getting more quality as time goes on or not. If this coverage number ever stops going up, the test is probably found whatever it's going to find. All right, so the thing to notice here is that our program panicked. That's the most common way for a fuzzing bug to be uncovered in Rust is a panic, not a crash, because Rust usually doesn't crash. And it shows us a message. This is the panic message. This is a out of range, out of bounds error, and the line that the panic occurred on. Then we get a big old backtrace. And finally, notice this output of standard debug. This is actually the input to the test. It's an array of bytes. So this particular array of bytes caused the markdown parser to panic. And that's likely a bug that we need to go fix. Also notice this at one of the last lines, the reproduce with, it tells us exactly the command to run to just run exactly that test case. So we can run that test case over and over, and I can even demonstrate that real quick. While we fix the bug, we can copy this here, and remember we have to use the nightly compiler, and we can just reproduce this test over and over. And then once we fix it, we go check in that bug to our CI, then go back to our fuzz test, maybe make some changes to the fuzz test, and keep fuzzing. That's all I want to say about Rust fuzzing. Oopsies. Now we're going to move on to Soroban fuzzing. Okay, so smart contracts are a special type of program, and there are some aspects of smart contracts that make them very desirable to fuzz, and other aspects that also make them a little complex to fuzz. In particular, smart contracts are very high security pieces of software. Any failure in a smart contract results in financial consequences. So any kind of testing we can throw at a smart contract, we probably want to invest in. So it's pretty desirable to use fuzzing as one technique of testing smart contracts. Smart contracts are also very small, so it's really feasible to have like full coverage of a smart contract. You might be able to expect a fuzz test to really find a lot of branches in a smart contract. Whereas a typical large-scale program, it would be very hard to explore the full program space. Smart contracts, though, are not just simple parsers. They can't deal with they can't deal with plain byte input. So when we test a smart contract, we need to have structured input, because a smart contract is a collection of methods that take typed arguments. And in order to do anything with that smart contract, we're going to have to convert bytes into typed arguments to do structured fuzzing. All right, so this next slide is just an example, like the basic stuff we have inside of a smart contract. You can see we have here a type and a set of methods. The struct here, time-bound, is a Soroban type, as indicated by the contract type Rust attribute. In Soroban, we can create arbitrary struct types. And here, this claimable balance contract is the contract implementation, indicated by the Rust attribute contract impl. This contract has a single method called deposit that we can call from our tests. This method takes Soroban types, like address and vectors, and our struct type. Important thing to notice here about this method is that the first argument is an inv. An inv is a really important part of Soroban contracts, and it's going to cause us a lot of complications when we go to fuzz test. In order to accomplish anything in the contract, you have to have access to an inv. That's the runtime environment. Even constructing Soroban values requires access to the environment. Again, the kind of types we're going to need to accept as fuzzing input include scalars and collections like strings and vectors and maps, and aggregate types like structs. So in the demo earlier, we just saw taking input as bytes, which is the natural language of the fuzzer. It just spews out bytes. But to accept structured input, we're going to have to use a little bit more Rust mechanisms, and that's what the SDK provides. This slide just shows a brief example of what we're going to be doing in order to accept Soroban values as fuzzing input. You can see here, the input to our fuzz target macro, it's no longer bytes. It's this like really wordy type, address as Soroban arbitrary : prototype. And I'll talk a little bit more about this in the next demo, but Soroban arbitrary is a trait provided by the SDK, and it has an associated type prototype. And so all Soroban values and all Soroban types have this associated type on Soroban arbitrary called prototype. And the fuzzer is able to generate these prototypes And then you combine that prototype with the env as shown on this slide to create your actual contract values. All right, next I'm going to do a little demo of fuzz testing, but with a Soroban example. Show a little bit more about these prototype inputs. Okay. So this example is out of the Soroban examples repository. It's also the example that is used by the Soroban fuzzing tutorial. So there's quite a lot of code here, and I'm not going to go through it in detail, but you can run this yourself through the tutorial. All right, again, a thing to notice, no main function here. And the most important thing is that our fuzz target macro, which is effectively the entry point of our fuzz test, no longer accept bytes as input. We're accepting this input struct. This is a struct that we have defined that defines all the structured input that we want our fuzz tester to be working off of. So you can see our struct input is defined here, and it derives arbitrary. Arbitrary is the stock trait used by Cargo Fuzz in order to convert bytes into structured Rust types. You can see we're importing arbitrary up here, these two lines. We're importing a bunch of stuff from the arbitrary module in the Soroban SDK. This arbitrary module is the home for all of the fuzzing support within the SDK, and it's well documented. One of your first stops when you start fuzzing Soroban is going to be just to read that module docs. You can see here there's a import from arbitrary : arbitrary. This is a re-export of the stock arbitrary crate. So the Soroban SDK, because you're going to need it all the time, provides direct access to the arbitrary crate, which provides the arbitrary trait. And again, the details are a little too gnarly to discuss in full here. But notice again, our struct input defines the first field address as an array here with the brackets, and inside the array, there's another big gnarly type here, address of Soroban arbitrary prototype. And again, that is the type that the fuzzer is going to give us that can be converted into a Soroban address. Also notice this next line, this is another arbitrary attribute. This is just a stock attribute that limits the range of this integer on the next line. It's not Soroban specific, but you're going to end up using these kind of attributes quite a lot in order to limit the range of integers when you're testing smart contracts. And finally, notice this last field is steps. This is a Rust vec. And here I've named this Rust vec disambiguate from the Soroban vec. The Rust stock vec is named vec, and the Soroban provides its own vec called vec. When you're writing Soroban contracts, you're often going to be using that Soroban vec, not a Rust vec. But then when you're writing test cases, sometimes you need a real Rust vec. And so good practice is to just give it its own name up here. You can say during the import, I've imported vec as Rust vec. That way it's easy to distinguish from the Soroban vec. The steps is a vector of steps, and the step is another custom struct that defines command. And it's just a sequence of commands to execute. So this fuzz test is going to receive a sequence of commands to execute, and it's just going to execute them in a loop. And again, I'm not going to go through everything, and it's a little unclear, but first thing you're going to do in a Soroban fuzz test is convert all those prototypes into concrete Soroban types. And I've got that in this example is buried in this config setup, so it's not going to be very clear what's happening. But if we look at config setup here, it takes this input, and you can see there's a couple places in here where we take those prototypes and we call, for example, address from val to combine those prototypes with the Soroban env to create a real Soroban address. And again, I'm going to go run this real quick. Cargo plus nightly fuzz run. This one's called fuzz target 2. It's going to be almost the same. And the Soroban example for fuzzing has an intentional bug, so you'll find the bug when you run the fuzzer. The only new thing to notice here is this output of standard debug, which is again the input to the fuzzer, is no longer just bytes. It shows structured Rust input. This is going to be very useful for figuring out what actually happened in any particular fuzzing iteration. All right. I think I'm going to go back to the slides. All right, so this next section is just a bunch of tips that I've learned about best practices for fuzzing Soroban contracts. Some of this was not obvious to me. Some of it differs from standard Rust fuzzing. And the first thing you're going to want to think about when you're writing programs to be fuzzable is you're going to really want to clear about what the distinction is between expected failures versus unexpected failures. So every program has many failure modes, and for any given input, there might be a lot of expected errors. If you feed me input I can't parse, that's an error. But it's not a bug. It's just expected error from the malformed input. But other failures, like a crash, that's a bug. Programs shouldn't crash. So unexpected failures are generally when the program takes some kind of branch with some kind of state that you didn't account for when you were writing the program and something wrong happens. And in order to have effective fuzz tests, the fuzzer needs to be able to distinguish between those two cases. It needs to say that this failure was an error and this failure was an exceptional error. Most modern programming languages, many modern programming languages, represent exceptional failures or unexpected failures as exceptions. In Rust, we also have a distinction between expected versus unexpected failures. In Rust, when you have an expected error, you're going to usually use return-based error handling, where you return a result, and that result is an error, and then you branch on that error and you handle it as normal control flow. Unexpected failures in Rust are generally handled with panics. Panics are essentially just like exceptions in Java. They immediately stop the normal flow of control and start unwinding the stack. Most Rust programs should never panic in normal operation. And so Rust provides us a way to think about expected versus unexpected failure by default. Unfortunately, though, this dichotomy between these two error handling mechanisms is a little cloudy in Soroban. And the reason is, in Soroban, there's a big emphasis on keeping smart contracts to a very minimal size. Smart contracts in Soroban are compiled to WebAssembly. And the more bytes your WebAssembly is, and the more bytes your WebAssembly executes, the more instructions it executes at runtime, the more expensive it is. So in most smart contract platforms, when anything unexpected happens, you just kind of want to terminate the transaction immediately and hand control back to the runtime instead of executing any more instructions. Because the more instructions you execute, the more opportunity there is for errors. And once something unexpected happens, you're already just kind of off the happy path. So the Soroban docs don't encourage you to use control flow and return-based error handling like standard Rust. They encourage you to handle errors with panics. So just every single error, whether it's an expected error or an unexpected error, you're going to panic, terminate the transaction immediately. Which makes sense, but the problem is that if you just panic on every error, then your test cases can't distinguish between these two different types of errors. So Soroban has a solution for this, and it provides its own macro called panic with error. And what you're going to want to do is you're going to want to use panic with error for all the error cases where you've explicitly accounted for it and you're expecting that to happen in the normal operation of the program. And you're going to save the panic macro for the exceptional cases that shouldn't ever happen. That way your fuzz test can detect those cases. When you panic with error, what happens is that you give an error code to the runtime to return to the caller, so the caller can introspect that error code and it can distinguish this is the error code for an unadorned panic, and this is the error code for an explicit error that I coded by hand. There's one more caveat in Rust. When we're talking about error handling, we always have to think about what happens on integer overflows. And this is true with smart contracts and normal Rust. By default in Soroban, with the way it's compiled, your overflows are going to panic. But again, that panic is a regular unadorned panic. And so in a smart contract, a natural way to handle overflows, and probably the way you're going to want to respond to every overflow, is to just terminate the contract. Like an overflow is a weird condition that is hard to reason about. So easiest thing to do is just terminate the contract and give up, or terminate the transaction and give up. But again, if you just let the default overflow handling do that, you're not going to be able to distinguish whether that was an intentional overflow or an unintentional overflow in your test cases. So what I would recommend at this time for overflow handling is that you always use the checked arithmetic and you handle that checked arithmetic explicitly. And if your solution for overflows is to just terminate the transaction, then you do a checked arithmetic and then map it to a panic with error. And you panic with error with probably a custom defined error code that says, okay, this was an expected overflow. And then that way, when your test sees, okay, this was an overflow, it can know, okay, this was an overflow that you explicitly wrote code for, and it was an expected overflow. And then you can catch all those times where you wrote plus but didn't really think hard about it. And if some kind of arithmetic in your contract overflows during a fuzz test, you'll see it and you'll be kind of compelled to go think about what happened on that overflow and whether it should be, how that overflow should be handled explicitly. Ooh, that was a mouthful. I hope that was clear. All right, the next tip I have is related to structuring of fuzz tests. And there's a number of ways to structure a fuzz test. There's kind of like a handful of 4 or 5 obvious ways to make a fuzz test. And the one that I recommend as being the easiest to kind of get started with and think about is to build a little command interpreter. A smart contract is a set of methods, and those set of methods can be called in any order with any combination of contract state. And so with a command interpreter, what I do on most of my Soroban fuzz tests is I create a little enum command, like we saw in our demo, and every variant of that command is maps to a particular method on our contract. So for this simple contract, if we have a contract where there's a deposit and there's a claim method, I create a command like on the screen here where one of the variants is a deposit and one's a claim. And then our fuzzer can generate just a sequence of commands, just call deposit, claim in all kinds of random orders with randomized arguments to those 2 methods. And then as you develop that fuzz test further, you can kind of augment this command interpreter with more ways of feeding strange combinations of arguments to these methods in order to exercise the state of the contract more thoroughly. All right, so Soroban contracts are compiled to WebAssembly, and most of the examples in the Soroban docs that I can recall generally encourage you to load that WebAssembly for testing. So you're actually testing the WebAssembly as it runs on the blockchain in your test cases. The problem with fuzzing WebAssembly is that fuzzing depends on this instrumentation of your code in order to track which branches are found. And that instrumentation doesn't carry over to WebAssembly compiled contracts. So as a fuzz tester, once you enter WebAssembly, it's just a black box and the fuzzer can't see what's happening. And with Cargo Fuzz, the fuzzer will even tell you, like, I've run for 1,000 iterations and I don't see anything happening at all in these test cases. Something is probably wrong. So fuzz testing WebAssembly is not going to be very effective. Fortunately, the SDK for Soroban provides 2 ways to compile your code. It can compile to WebAssembly, but it can also compile all your contracts to native host code like x86 or ARM. And when it does this, you can instrument it for fuzzing. So these next 2 slides just show the difference between the 2. When you're loading a WebAssembly contract, you use the special macro contract import and load the actual WebAssembly, register it with your test environment. Native compiled contracts, though, you can just use like any old Rust code, import them from a crate, and then register that native code into your contracts. And this works with any number of contracts, whether you're testing a single contract or testing an entire constellation of contracts. All those contracts can be compiled in native code and then registered as native code. All right, so this next tip is really obvious, but it was at least 4 months before I figured this out, so other people might miss this as well. The way you interact with a contract, whether it be from another contract or from a test, is through that contract's client. Every contract has a specific client for calling it. And that client manages the marshaling from one environment into the contract environment of all the arguments and things like that. But these clients are generated code and not handwritten. You can see on this slide, we have a contract on the left-hand side, my contract, with the contract impl annotation attribute. And that contract attribute handles all the generation of these clients. And because clients are generated code, they're not well documented, and it's not obvious what they're capable of or what they do. The basic thing they do, though, is they generate a method on the client for every method on the contract. So in this example contract, we have an add method. And on the right side, we have a client that can call the add method. You call the add method on the client, it handles all the work of calling the add method on the contract. But the way these default methods, the just plainly named add method here, handle errors is to panic, which in some cases is desirable, and it's kind of the safest thing to do by default. But panics are not easy to interpret in Rust. It kind of can be done, but it's pretty ugly and non-standard. But fortunately, these clients also, for every single method, they generate a second method with a try underscore prefix in front of it. This is kind of a standard pattern in Rust, the try prefix. It says, do this thing and give me some kind of handleable error if it fails. So in this case, the try-add method is going to return an error if anything goes wrong while calling that method. That error is much easier to introspect. Importantly, we can introspect it to figure out, was the error panic, an unexpected failure, or was the error something that we coded and was an expected error? It's much easier if you're using the try methods than the standard methods. Next, with all your contract testing, you're going to want to think about the role of time. Tests kind of just run real fast in one shot instantaneously, but that's not how programs work on the blockchain. On the blockchain, your contract will run a transaction, then it'll wait some unbounded arbitrary amount of time, then it'll run another transaction. In between those two transactions, essentially the entire world is destroyed and reconstructed from scratch. The testing environment, the runtime environment, does not persist from one transaction to the next. And you're going to want to think about the effects of this in your fuzz tests as well. And there are a few ways to advance time in Soroban tests. The simplest one, which is in most of the docs, is to kind of just take your test environment and frob the sequence number, the block number, so the environment sees that we're now at a different timestamp and a different sequence number. And this seems to work, but it makes me a little uncomfortable because just advancing the block number is not really all that happens between transactions in the real world. In the real world, that VM is destroyed, the environment's destroyed, everything's serialized out to the blockchain. And the next transaction, it's all reserialized into the environment is reconstructed, and everything starts from scratch. So that's what I tend to do when I do testing of smart contracts. And this slide shows a little example of how that can be done. I'm not going to go into it, but this code also exists inside of the Soroban example for fuzzing, and you can find it there. Okay, finally, fuzz tests are kind of ephemeral. You often write fuzz tests, find what they're going to find, and throw them away. But there's something pretty cool we can do with Soroban's fuzz tests, and that's we can convert them to a simpler type of test called a prop test. And a prop test is similar to a fuzz test, but the big distinction is that prop tests are just normal Rust unit tests. They live next to all your other Rust unit tests, and they can be checked into your Git repo and then run as part of CI. Prop tests, though, are weaker than fuzz tests. The big difference, the big thing that makes them not as strong as fuzz tests is they don't have that instrumented feedback cycle. Prop tests don't have any insight to what the program is actually doing while it's testing. It just kind of naively, well, not naively, but it generates the input based on the types that it's accepting as input. It doesn't change the inputs based on what happens when the tests run. So it tends to not find as rich a set of results as a fuzz test, but if you write a fuzz test and it's a successful fuzz test and finds a lot of good bugs, I highly recommend converting that fuzz test into a prop test as a kind of regression test for that set of test cases. And this slide shows the basic transformation between the two. Again, this is covered in the tutorial, so there's no need to really go into it here. All right. So in the course of developing this fuzzing support for Soroban, I have tested some example contracts, some real-world contracts, and I've even done some fuzzing of the Soroban runtime itself. I'm not really prepared to talk about most of that, but I am prepared to talk about probably the most fruitful results we've had, which was in testing the Soroban runtime itself. So in Soroban has its own type system where it defines things like integers and addresses and collections. And this type system is defined through XDR. XDR is the serialization format used by Stellar. But at runtime, the Soroban type system does not use that XDR representation. Like contracts don't operate on XDR, they operate on a compact in-memory format, which I might call contract values for the sake of talking about it. But importantly, there are parallel hierarchies of types in Soroban. There's the XDR types and there's the contract types. And these have to be perfectly in sync with each other. You have to be able to interconvert in both directions from XDR to contract and back to XDR again. And importantly, the comparison functions of all these types must be exactly the same. So if you compare two XDR values or two XDR addresses, and then you compare the two equivalent contract addresses in the contract space, the comparison functions have to be exactly the same. And this is not just true of like values that have the same type. Like if you compare, in practice, it is possible to compare weird combinations of types. So if you compare an address to a vector, for example, that has a logical result, a real result that makes some kind of sense. And that result has to be the same in the XDR world as in the contract world. And all this is kind of like hand-coded and has to be perfectly in sync, or there are security consequences. And so if you remember, one of the slam dunk cases for fuzz testing is when you have multiple representations of the same type. So I was super excited to discover this about Soroban runtime because it's easy to fuzz. So we created a fuzz harness that just generates all kinds of random XDR values and then all kinds of random contract values. Converts back and forth in both directions, make sure that the values round trip, and then runs the comparison functions on both sides of the conversion and ensures that the comparison functions have the same result. And this was super profitable because we found 2 or 3 bugs and they all got fixed. And then we converted that fuzz test to a prop test, checked it in, and hopefully that bug will never come back in Soroban. All right. All right, so some of the important things to remember about fuzz testing in Soroban. We use the Cargo Fuzz tool. It's the standard tool. All the SDK fuzzing support is in the arbitrary module of the Soroban SDK crate. It's got lots of docs. Go read those docs. All Soroban types can be accepted as structured fuzzing inputs. That's even custom types, using this Soroban arbitrary trait and the prototype associated type on that trait. Effective fuzzing requires programs to be written with careful attention to the distinction between unexpected failures and expected failures so that the fuzz test can distinguish between the two. And fuzz tests can be converted to prop tests to check in with your CI. All right, on your screen here is the link to the official fuzzing tutorial. Again, it contains much of this material and hands-on stuff so you can go read in more depth about some of these topics that I didn't go into here. And that's my talk. Thank you for coming. I can take questions if anybody's got any.
So much. That was fantastic. Very detailed. We got the demo this time. It was amazing. Yep. One question, and I think this one came from Morgan. And when you're running those fuzz tests and you're putting in the inputs for the arguments, and then you run the fuzz test, it's just whatever your type is. It's just putting in every possible variant of that type's value, right? So you've got the I-128. Every time it runs one of those fuzz tests, it just picks an arbitrary another value that's a viable value from that type and inserts that into the execution. That's right, correct?
That's essentially right. It's a little more involved in that, and that like the fuzzer itself doesn't really understand your Rust types, so the fuzzer isn't sending you like every variant of a Rust enum. It doesn't understand Rust variants. it's just throwing bytes at the program. And then there's this arbitrary trait that's written in Rust that takes those bytes and tries to intelligently spread those bytes out and give you all the variants. But it's not so intelligent that it's just going to go down a list and just give you all the variants.
Right. That was the only one that I'd seen in the actual chat. If anybody else has questions, feel free to ask. I would actually, if you can, I just told you to turn off the screen, but if you could go back and actually solve the issue in that second one, I feel like there's a couple of different ways, but it might be really interesting to go through the process of how you would actually you have the route that actually errored, so you know what you need to rerun once you try and fix it. So are you able to go into the code there, figure out what the actual error is, and fix it, and then rerun that particular crash so that it would pass?
I can probably do that. I have not practiced that, but it's pretty obvious where the bug is. I'll try to walk through it in a way that makes sense, and I'll probably make some mistakes. I'll probably fumble this a bit. So again, this is our crash that we found the bug in our Soroban contract. And I'm not going to look at any of this back scroll yet, but we might be able to find some useful information in it. First thing you want to do when you find a bug is take this reproduction here, reproduce with. We're going to copy this command and get it on our command line and get it in our command history, because we're going to be running that command over and over as we try to solve the bug. All right, so I've copied the command, and again, I've added the plus nightly to it. This is just going to find that exact same error over and over. One thing to note is that when I do the repro, I don't get that kind of big brain dump of all the inputs and things like that at the end of it. So this repro only shows me the backtrace. So if I want to see like this information, I'm only going to get it once. That's kind of unfortunate. But like in the original run that we found the bug, this output here, which is the input to our fuzz tester, this is very useful information, and you're not going to get that again as you do the repro. In this case, I don't think this information is going to help us, but in a lot of cases, you can kind of scan through it and see, okay, this is a weird combination of inputs. See, in this particular input, our steps, remember our steps is our commands for our command interpreter. This particular input had one step in it. So we advanced time by some number, and then we did a deposit. So this is a deposit step. And somehow this deposit triggered an error. I'm going to note that this advanced time is not particularly weird, right? Sometimes you advance time and it advances time by 1 billion blocks, and it's like, okay, that's weird. Maybe I did something wrong with that amount of time. I also note that this deposit has a 0 in it, so we're trying to deposit 0 tokens. And I think none of this else is really interesting right now. So I'm going to go back to our test here. And this is our fuzz test, but this is not our contract. Our contract here is in this Soroban fuzzing contract crate, I hope. Again, I haven't looked at this in a while. For the Soroban examples, you can see I'm in the Soroban examples repo. And this is the fuzzing example right here. And within the fuzzing example, fuzz is our fuzz tests. And fuzz test is its own cargo project here with its own manifest. So all of our fuzzing stuff is in this fuzz directory, but our contract is in the source directory. So lib here is our contract. And this contract is the time lock contract that's used in another Soroban example, but it's modified a bit to illustrate some of the fuzzing details. And so I know this was a deposit, so I'm going to go look at the deposit. This is our deposit method. Again, we also have a claim method, but this was the only thing that happened in this test was a deposit. We deposited 0 tokens. And I note here, the example has this commented out code, suspiciously, that says, maybe we don't want to accept 0 tokens. So I happen to know that if we uncomment this code, we're going to fix this particular bug, and we're going to reject 0 token deposits. Now I can just take this same repro and do the repro again, and it's going to recompile that. It's going to take a bit of time. This is an underpowered laptop, but we're going to recompile this contract and try to run the fuzz on the changed contract. I didn't look through this backtrace, but in this case, the backtrace, we kind of figured out everything we needed to know just from looking at the input. All the backtrace is going to tell us is Rust backtraces honestly take some practice to learn to read because there's so much goop in them. You can see here at the bottom of the backtrace, this is kind of near the entry point. This libfuzzer test1 input. This is the kind of the fuzz test running, or the fuzz harness running. And this panicking try is kind of inside of the Rust standard library where it's going to catch panics, because panics are going to be an indication of a test failure. We've got a bunch of more Rust runtime goop. And finally, this Rust fuzzer test input. This is the function that fuzz target macro generates. So this is generated code, but it's going to be calling our closure that we passed to that macro. And if we keep going up, see that eventually somewhere in here there's going to be a call to deposit. But I am not going to sift through all this noise right now. Okay, so in that time, our test finished running. And you can see here there's this message, like it looked like nothing happened, and it says fuzzing was not performed. That means that like the test case succeeded and it didn't do anything and nothing interesting happened, which means the bug is fixed. So now we can go check that case into our tests and continue fuzzing with the normal fuzz input. There you go.
Fixed. Appreciate that. Amazing. The only other thing that I know that I would really like to look at is something when I was looking at fuzzing, it was super interesting, was the arbitrary tags when you can essentially bound input fields. So it might be good to kind of highlight how you might customize some calls to your types. Like in the case of I-128s, for example, you may not want it to be negative numbers, but it's still a type that includes a bunch of negative numbers. So how do you bind using that arbitrary to only include like 0 through the max?
Yep. All right. So there's a number of ways that the arbitrary implementations have been customized. And I got a few things I'd like to point out about this. The first thing I'll note is that the Soroban values, including your Soroban structs when you define your own structs, they're going to automatically get an arbitrary implementation. So with Soroban, you're probably never going to be writing your own arbitrary implementation. Also, if we go look at our fuzz target, you'll see we derived arbitrary on all these structs. Almost always you're going to be deriving arbitrary or using the existing arbitrary implementations for Soroban. But those derives, when you derive arbitrary, there's ways to customize them. So this arbitrary attribute here is interpreted by the derive macro for the arbitrary trait. So there's a number of ways to customize the arbitrary derivation using Rust attributes. And honestly, I always forget all the details, but one of the things you're going to want to do is go to the arbitrary crate docs. With Rust, the crate docs are always easy to find. Go to docs.rs/arbitrary. This is the standard arbitrary trait, or the arbitrary crate that defines the arbitrary trait. And the arbitrary crate docs are okay, not great. I found that sometimes it's hard to find what I'm looking for in them. But you can see the arbitrary trait is pretty well documented. And what I'm actually looking for right now is the docs that explain what those attributes do, because you're going to need those, because I never remember what the syntax is, and I always have to kind of copy paste and look at the docs for them. And what I think you have to do to find those docs is go to the GitHub repository and look at these examples. Here you go. So this is a thing that is a little awkward about the arbitrary trait docs, or the arbitrary crate docs, is that not all the docs are in the crate. Some really important docs are in GitHub. So here you can see a number of examples of customizing the arbitrary derive. You can tell it just give me the default implementation. So in here, you're not really getting random values, you're just getting the default value. Here you're saying an exact value. And here you can say, use another implementation of arbitrary. I'm not exactly sure what this means. I've never used this. But what we did in this Soroban example was this method, where it's just give me some closure, and it takes this closure that you specify in an attribute and converts that closure to code in the derived arbitrary implementation. So this is just a closure that takes this unstructured type. Unstructured is the type in the arbitrary crate that provides access to all those random bytes that come from the fuzzing input and allow you to do something to convert those random bytes to Rust types. And frankly, the thing you're going to want to do a lot is exactly this, is just limit the range of integers. So I always come back here, I just copy this and paste it over there. But since this is a closure, you can literally do whatever you want in here. Just look through our code real quick. I think that's probably the only way I use this customization, is just to limit the range of integers. See, there's more here. Yep, that's everything I did with that. Again, I myself just have to go read the docs every time I want to do it.
Fantastic. Yep, that one was super cool when I ran across it. Last question here. This one was from Elliot. He's asking how you would turn that 0 for deposit into a prop test. My guess is that would probably just be a unit test because it's a hard-coded value of a 0 for a deposit.
Yeah, that's a good insight. So generally, once I find a bug with a fuzz test and I fix that bug, I will generally write a focused unit test that captures that exact input. So in that case where there's a 0, I would write a unit test that just tests for 0 deposit. But I also convert the fuzz test to prop tests. So every individual bug a fuzz test finds, I'll write a single unit test for that individual case, but a fuzz test might find 5 different bugs. They all have different fixes and require their own unit tests. And then you can take that fuzz test and convert it to a prop test that kind of does the exact same thing the fuzzer did. So you kind of get double the coverage. Just a little thing to note, though, is that the fuzzer doesn't really help you write unit tests. So when you find a single input to the fuzzer, the fuzz tester gives you a command to reproduce that through the fuzzer, but you can't check that reproduction into CI in an easy way in order to just like capture the unit test as it was found in the fuzzer. You got to kind of go handwrite that unit test. As to the actual question about converting this particular test to a prop test, honestly, I don't think I can do it live because I don't remember how to do it, but I can kind of talk through what I would do. So remember our source code for the crate itself lives here in fuzzing/source. So here, okay, actually, it's already been done in this example. We have a prop test. Remember, your fuzz test lives in its own crate. So when you convert it to a prop test, you're going to be transferring that code into the crate that you're testing. So we're moving that code from the fuzzing crate over into our actual contract crate. In this case, I've created a whole module for prop tests. And in our prop test module, the code is going to be almost exactly the same. So if you look at this, it's almost entirely identical. We don't have to change much to do the prop test conversion. Unit tests are not their own program. So again, we don't have no main, but instead we've used this test config. This says only compile this module when we're actually testing. Don't try to compile this module when we're compiling the contract. And you got to do that for Soroban because the testing is going to use the standard library. And Soroban contracts don't use the standard library. So in Soroban, you kind of got to really be careful about configuring your test code to not compile when you're compiling for production. Here we imported the prop test prelude, and we also imported this arb function. I think this is a function. The prop test arbitrary interrupt crate. Prop test arbitrary interrupt crate is kind of the key for converting fuzz tests to prop test. Or a bit. Did I spell that right? So this crate is just a little bit of glue between the arbitrary fuzzing world and the prop test world. This crate was created by our own grade and whore, and it's pretty simple to use. You can see we have a prop test here. I'll just go back to our code and look at that. Here is where we probably would have said fuzz target, the fuzz target macro. Just looking at this and seeing how similar these actually are. So basically, you're going to replace the fuzz target macro with the prop test macro. And this attribute here says how many cases we want to run. Here we said 100, but you can say as many cases as you want, as many iterations. But in the prop test, we're probably going to run very few tests because it has to run quickly for CI, whereas the fuzz test, you're going to run a lot of test cases. And as the input, the only real difference here is that we're going to say, this is how we specify the input to our prop test, whereas over here, this fuzz target closure input is the input to our fuzz test. But they both accept input. It's just that in the prop test, you use this. And this is not Rust syntax. This is prop test macro syntax. So this input in arb input is calling the arb function with input as a type. And that's going to do the mediation between the prop test world and your Rust values. And I note that the actual code inside fuzz target and prop test is not quite the same here. Probably I iterated on them separately and didn't end up at the same place. But that's basically the whole thing, is you just convert the entry point from this fuzz target bang to prop test bang. It's very mechanical. The example is in here, and the example is also in the fuzzing tutorial. So really what you're going to do is just go look at that example and kind of copy paste in order to do it. Okay, there you go.
Fantastic. That was amazing. Yeah, the conversion between writing the fuzz test and then converting it into the prop test was especially when you see like the with cases for the number of times you just want to iterate over some arbitrary values, super cool. My mind was definitely blown when I finally understood this and got it to run.
Yep. Prop tests are a powerful tool in their own right, not just for converting from fuzz tests. Really a way to get really powerful unit tests without the full power of fuzzing.
Yep. Well, Brian, thank you so much for taking time out of your day to come and hang out with us, for writing all of this functionality into Soroban. Hopefully it'll be really valuable to folks. Hope to see you around as you continue to contribute. Your contributions have been really valuable, and we appreciate your time. As people do have questions, Brian is definitely around on the Discord. So as you are writing your fuzz tests, you can send them to him. He'll write them for you, I think.
Yeah.
But we appreciate everybody hanging out. If anybody did have trouble with video feeds or anything, I should have this recorded. We'll get a VOD up, and you can just replay it at 2x speed or half speed, as the case may be. But everybody have a fantastic rest of the week, and we will catch you all later.
Thanks all.